Alright, welcome back. Today we're looking at, we're starting probability, 13A, sample spaces and probability. Now, again, this exercise is really a recap of things that we looked at in year 11. So, a lot of this stuff I did explain in previous years in more detail. This is, basically a revision chapter for year 12. Um, Obviously, we need to remember that if we're talking about probability, we're looking for values between 0 and 1. 0 meaning it's impossible, and 1 meaning it's definitely going to happen, it's certain. If we're asked about sample spaces and events, again, we could be conducting a random experiment with a six-sided die. If you're asked to list all of the possible outcomes, what you would be doing is ultimately listing out the sample space. Yep. So with a regular six-sided die, the sample space is denoted by the Greek letter epsilon, and you would actually write epsilon equals, so the sample space is equal to, notice here we're using braces, the curly brackets, so braces, and we're listing out each of the possibilities as the sample space there. You can roll the numbers 1 to 6. Happy days there. Again, if you are asked for a particular event, that's usually a subset of a sample space. So for example, if they said, hey, event A is an even number with a six-sided die, you could write out A is equal to, and listing out that event. Obviously it's 2, 4, and 6 there. It says here, if A and B are two events, then the union of A and B is written as A, here's the union symbol B, is equivalent to either event A or event B, or both occurring. Some other things that we can talk about. So you could be asked, if find an even number with when a six-sided die is rolled, is event A, and event B being a number greater than 2. When a six-sided die is rolled, obviously you can list out each of those events. Event A was the even numbers, event B was the numbers greater than 2. The union of those is obviously the numbers in both of those spaces and in A and B. Yep, so combining them. Again, the intersection, if we're looking at this particular Venn diagram, is denoted as A intersection B, and it's equivalent to both A and B occurring. So that's the intersection was where they overlap in the middle. So you can see here in this particular case, the intersection of A and B is 4 and 6. Yep. So often it helps to draw these types of diagrams, and we can also draw tree diagrams as well. So example 1 here says find the sample space when 3 coins are tossed and the results and note the results. So again, hopefully you realize with the coin, if you're tossing a coin, it's either going to be heads or tails. So if you toss the first coin, obviously you're listing the items there, heads or tails. From there you create the branches of the possibility. So in the second coin toss, after the head of the first coin toss, there are 2 branches. Again, you could get heads or tails again. And likewise, if the original toss was tails, you could have on the second toss heads or tails again. Continuing that notion, you can create the branches, obviously for the third coin. Again, it could be a heads or tails, following on from each of those events. Now, when you are asked to list the sample space of the 3 coin tosses, you would follow each of these branches here and list all the possible outcomes. So you could get heads, 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 writing out that as a possibility. You could get heads, heads, tails, and I guess you could follow the message there and list each of the other outcomes. When you are asked to list obviously the sample space, it's all of the possible outcomes. So again, using epsilon, which is sample space, and writing out all of the possibilities there using the comma there. Next thing is you could be asked to determine the probabilities in this particular case with equally likely events. So when they are equally likely, the sum of them is all going to the sample space is going to add up to 1. So again, when we're talking about the fair die, it's equally likely to roll each of the numbers 1 through 6. you can see here when we each of those is equal to 1/6, the probability. If you add each of those sample spaces together, that would be equal to 1. Please remember as well, when it says when the sample space is finite, the probability of an event is equal to the sum of the probabilities of the outcomes in that event. So it says here, let A be the event that an even number is rolled on the die. So we've listed that there. And so therefore the probability of A is equal to the probability of getting a B plus the probability of getting a 4 plus the probability of getting a 2. Oh, sorry, a 6. And obviously that in this particular case is equal to 1/2. Again, it's probably easier to calculate it just using the total number of outcomes in A divided by the total number of outcomes, and that can be simplified down. So that information is really gathered here, which basically says the probability of A is equal to the number of outcomes in A divided by the number of outcomes in the sample space. Some other rules that we have with probability. It says here the probability of A has to be greater than or equal to 0 for all events where A is a subset. Remember, this is a symbol for a subset, where A is a subset of the sample space. It says here the probability of the set is equal to 1. Yep, so everything together has to equal 1. It says the sum of the probabilities of all outcomes of an experiment is 1. Yep, we've spoken about that. Probability of an empty set, this here is an empty set or null, is equal to 0. I'm remembering as well from year 11, A dash means the complement of A, and the complement of A is basically saying not A, and that can be calculated as 1 take away the probability of A. So that's useful to remember. Again, the last one that comes up a lot is the addition rule, where you've got the probability of A union B is equal to the probability of A plus the probability of B take away the probability of A intersection B. So if we think about the Venn diagram, it's adding both A and B parts together, but making sure that you subtract the intersection part because it overlaps. Another thing that you need to remember is where two events A and B have no outcomes in common, so there's no intersection in the middle, they are known to be mutually exclusive events. If you know that the events are mutually exclusive, then there's nothing. The intersection between them is equal to 0. Yep. And so in that particular case, because the intersection is 0, the rule for A union B, when they are mutually exclusive, is just adding the probability of each of those events. Cool, let's have a look at the next example. It says here, cards, cool. Again, these pop up a lot. You need to know that there's the 52 cards in a deck. You need to know there's the 4 suits, etc., etc. If one card is chosen at random from a well-shuffled deck of 52 cards, what is the probability that the card is A and ace? Yep. So again, we know that there are 4 aces in a deck of cards. So again, there's going to be 4 out of the 52 sample space. Again, that can be simplified down to 1/13. This one here, probability that the card is not a heart. So there's a few different ways you could calculate this. You could have the amount that are not hearts out of 52. Or the other way of looking at this one is saying, okay, well, what's the probability of it being a heart? Probability of it being a heart is 13 out of the 52, which simplifies down to a quarter. But we're not after the probability of a heart, we're after not a heart, which is H dashed. So remember the rule for H dashed. It's obviously 1 take away the probability of H in this particular case. So 1 take away the quarter is 3/4. Next one, it says here, what is the probability that the card is an ace or a heart? Okay, so what we're looking for here is it's an ace or a heart, so it's A union H. So again, that is where we can use the addition rule. Yeah. Now, in this particular case, we need to know that you can have an item that is an ace and is also a heart. Yep. So we have to use the addition rule. They're not mutually exclusive. They can occur together. So using the rule, probability of A, so the ace probability of the heart, take away the intersection of those. As we've said before, the probability of A intersection H, so being an ace and a heart, there's only one of those cards in the deck, so 1 out of 52. So therefore, using the rule, we worked out what the probability of ace was in part A. It was 1/13. Worked out what the probability was of a heart was 1/4. Applying the addition rule, we take away this 1 over 52, and we end up with the probability of A union H is 4 out of 13. 4/13. Last one was either a king or an ace. Again, you cannot get a king and an ace at the same time. They are mutually exclusive. So therefore, we can consider that when we're working out the addition of those. So basically saying it cannot be done, it's null, it cannot be intersection of those. They're mutually exclusive. So to find out K union A, it's just the probability of K plus the probability of an ace. So probability of king, and a probability of an ace. Add those together and it's 2/13. Alright, next one, example number 3. It says here 500 people were questioned and classified according to age and whether or not they regularly use social media. They've created a table. Perfect. Again, you'll notice this one has the age less than 25 listed here, where it's greater than or equal to 25 here. They've listed the totals for each of these sides and the grand total obviously down the bottom here. So it says here one person is selected from these 500. Find the probabilities that. It says the person regularly uses social media. So again, the question was, do you regularly use social media? And we're saying they do. So we're looking for yes here. The total for yes is listed across over here. You follow it across. The total that said yes was 300. So obviously work out the probability. There were 500 in total, so it's 300 out of the 500, and we can simplify that down to 3/5. Next one, it says here the person is less than 25 years of age. So again, we're looking here at this particular column. Age was less than 25. The total of those is here. There was 240 out of the 500, which does simplify down to 24 out of 50 or 12 out of 25. Last one says here, the person is less than 25 years of age and does not regularly use social media. So again, they're less than 25, so we're looking here, and they do not regularly use social media, so they said no. So in this column, the no was listed here. It's 40 out of the 500, obviously, which simplifies down to 2 out of 25. It says here there are other methods of determining probabilities, and it says here one of the ways is just to use a subjective probability, so where you can just assign a value based on a judgment. So the example they've used here is a farmer may look at the weather conditions and determine that there's a 70% chance of rain that day and might take appropriate actions. That's their best judgment. That's just called a subjective probability. Another way in which you can work these probabilities out is to collect data and make some judgments based on some data. So again, you could do a random experiment and record those results, and you may have done coin tossing and dice rolling and recorded results in the past, and obviously doing those trials, you'll collect a relative frequency of these events. It says here relative frequency of an event A is the number of times the event A occurs divided by the number of trials. And so again, when you have a sufficiently large number of trials, the more you do, the more accurate this is going to become. So it's saying basically that the probability of an event A is approximately equal to the number of times event A occurs divided by the number of trials, where you do a large enough number of trials. Yep, you can't just toss a coin 3 times and go, okay, this is enough data. The more times you do that, that would be better. Good news is someone has done the experiment for us, and they've tossed the dice 1,000 times, and they've recorded the frequency for each of those outcomes. Perfect. We didn't even have to do it. They've done it for us. So in this particular case, it says use the information to estimate the probability of observing a 6 when the die is rolled. So again, you can see here where the 6 was rolled, it happened 97 times. So using the formula above, we say we can put the number of events of 6 divided by the number of trials, which we did 1,000. So probability of getting a 6 is going to be approximately equal to 97 out of 1,000 based on this here, which is 0.097. It then goes on to say, what outcome would you predict to be the most likely to occur on the next time the die is rolled? So again, if you're looking here, you're looking at which one of these outcomes had the largest number, or largest sort of frequency. So here, the largest frequency was 280, and it occurred with the number 3 being rolled. So I would say in this particular case, the most likely outcome based on this data was 3 because it had the highest relative frequency. This is interesting. You can get the probabilities from an area. So again, it says when we use a model of equally likely outcomes to determine probabilities, we count the outcomes in the event and the outcomes in the sample space and use the ratio to determine the probability of the event. It says this can be extended to calculate probabilities when areas are involved by assuming that probabilities of all points in the region which can be considered the sample space are equally likely. So example 5 sort of takes this on board, and it says here we've got a dartboard, and this is not your traditional dartboard. They've got a dartboard that's it's a square that's 2 meters by 2 meters, and it's got a 1/4 of a circular disc centered at the bottom left vertex of the square as shown. And so they're saying here you can throw it at the dartboard, and they want to know if the dart is it's thrown at the square and it's equally likely to hit any part of the square. Find the probability of hitting the blue region. So again, what you need to do in this particular case is work out what the area of the blue region is. So we've got a circle, and it's a quarter of a circle, so a quarter times pi r squared. We can get that this area here is pi meters squared. The area of this particular dartboard was 2 by 2, which is 4 meters squared. So the probability of hitting this blue bit is the ratio between them. So again, it's the area of the blue region, which we worked out was pi, divided by the total area here of the square, or the whole dartboard, which was 4. So the probability of hitting that blue region was pi on 4. These are pretty cool. Probability tables are an alternative to the Venn diagrams. We've been looking at these Venn diagrams here. You would have seen this before. The intersection of A and B, A intersection B dashed, so forth and so forth, not A and not B over here. You can use this Carnot map. And here is how the probability is listed. Again, that can be expanded upon whereby you're going to get the total of A listed here, total of not A, or the probability of not A over here, probability of B listed down here, probability of not B listed here. And also note that the total of getting both probability of A and not A is 1. Likewise, probability of B and not B is 1 as well. Yep. So these add together. And again, this can be useful knowing that the sum of these columns add up to each of these, and the sum of the rows add up to these. You can use it to solve some questions where pieces of information are missing. So an example of that is as follows. We've got Simone. She visits the dentist every 6 months for a checkup, which is good for her teeth. It says the probability that she will need her teeth cleaned is 0.35. The probability that she will need a filling is 0.1. The probability that she'll need both a filling and her teeth cleaned is 0.05. Cool. So based on this information, you can start to create the table. So again, we're denoting C is clinging teeth, F is filling, obviously F dash is not filling, not clinging teeth is C dashed. So creating the table, remember we said down the bottom right hand corner, these totals have to add up to 1, so you're going to put a 1 here. We're going to put in the information that we do know. So this probability that her teeth needed to be cleaned was 0.35. So teeth cleaned, probability of that is 0.35. We're going to list it here. Likewise, that she needs a filling is 0.1. Filling, probability is going to be listed down here, 0.1. Probably that she needs both a filling and also cleaning her teeth. So cleaning your teeth and filling is in this section here, 0.05. We can list those there. From that information, we can now use our basic math skills to fill in these gaps here. So we know that this here plus this one here have to add up to that. So you could do this, take away this, get that one and fill it in. We can also use our skills to fill this one in using the same knowledge. We've got all these listed here. You could then know that this row has to equal 1. You can do 1 take away 0.1, gives you that there, so forth and so forth. Eventually you can fill out all this table here and know that information, which is good. Get that table set up and then you can answer the types of questions they ask. So it says here, what is the probability that she will not need her teeth cleaned on a visit, but will need a filling? Okay, so not need her teeth cleaned is F dashed, but she will, not need her teeth cleaned will be C dashed, and she will need a filling. So filling and not her teeth cleaned, it's going to be 0.05 there. Next one says here, what is the probability that she will not need either of these treatments? So that's either C dashed and F dashed. C dashed and F dashed is 0.6 there. Here is the section summary, which outlines all of the things that we spoke about. Again, this should be a revision from year 11. Take care for now. Bye.